This is the first in a series of video lectures about context-free grammars. It's CFG for short, so this slide is called CFG1, which is a basic introduction to the concept of context-free grammars. So far we have seen how we can build a lexical analyzer, and it produces a stream of tokens. And these stream of tokens now we're going to use in order to build the structure of the program. And that's the job of the parser. So the parser is what we're going to focus on as the next step in building a compiler. And in order to understand how the parser works, we first need to understand how context-free grammars work, which is kind of the topic of these video lectures. The way that a parser interacts with the lexical analyzer is that it asks for the next token. The lexical analyzer gives the parser that token, and then the parser then asks for the next token, and so on. And if it's a valid program, it produces a parse tree, which is then passed on to the later stages of the compiler, the backend. In Flex, the next function, the function that the parser uses to ask for the next token is called yylex. And every time it calls yylex, it'll get the next token in the stream. The lexical analyzer is responsible to produce all the lexical errors, and the parser is responsible to highlight the syntax errors, if any, in the program. So the parser's job is not to allow any invalid program through to the code generation part. So it should only produce code for a valid program for that programming language. So one of the jobs of the parser is to figure out whether the program is valid or not. So if you look at every possible sequence of tokens, not every possible sequence is valid. So the parser's job is to distinguish between valid and invalid programs. So what do we need for this in order to accomplish this goal? We need a language for describing a valid sequence of tokens. And we also need a method for distinguishing valid from invalid programs. We need some kind of algorithm. And in the end, we need some kind of data structure that will provide the structure of the program if it's a valid token sequence that we can then pass to the subsequent phases of code generation, semantic analysis, etc. So we need to do these steps in order to begin to write a parser for a programming language. The concept of a context-free grammar arises when you notice that programming languages have recursive structures. Let's look at an if-then statement in a programming language and how we can actually embed other statements or expressions inside it. So let's start with an if statement here. Then we know that inside, if the expression is true, then it can do some sequence of statements, and it could have inside it a while loop. Now inside the while loop, it does a while do, and inside the while loop you might have an if statement. So you notice that the if statement is appearing again nested inside a while, which is nested inside a if. And then further, you can nest a while loop inside it. And this is perfectly legal in modern programming languages, right? You might need to do an if statement and then do a while statement inside it and so on. So when you observe this kind of nesting structure, you can kind of abstract away from the specific statement reserved words like if and while, and just think of them as parentheses. So here's an open parentheses if, which should match the closing sort of the else statement that matches that if, right? So just to abstract away from the complications of all of programming language syntax, I'm just going to use an open parenthesis and a close parenthesis. Similarly, I can have an open parenthesis to represent the start of the while and a close parenthesis to represent the end of the while. And if I keep going, I can see that I have this kind of nested structure in here where these parentheses have to match up to each other. And if you look at this series of nested parentheses, it turns out a context-free grammar, which is what I'll explain to you in the next several slides, are a natural notation for these recursive structures. It's sort of a natural fit for the recursive structures we find in programming languages in particular. Now you might ask the question, why do we need context-free grammars? Why not just write a regular expression to do this job? because we've already learned about it and we know how to use it. Why not just use that? It turns out a finite state automata is unable to handle nested parentheses. So you might say, well, Anoop, I don't believe you. So let's try and write a finite state machine that tries to recognize parentheses. And let's just do a NFA. So let's say that I can accept on this start state. So this is my start state, and I can accept as many open parentheses as I want. And then I have a transition to state 2, and there I match all of the closing parentheses. So, and then this could be my final state. So notice that it does match valid strings like open parenthesis, close, and close. This would work, right? But the problem is if I have 2 open and 1 close, this will also get accepted. And it shouldn't, because it's not a valid program. Like if this was an if statement and then a while statement, and then you don't have the else statement or the ending of the if statement to match the opening, that means it's not a valid program, right? So it turns out, because of this notion of a finite state machine where it doesn't have any memory, it cannot memorize how many. So it cannot really figure out how many open parentheses were collected in state 1 before it went on to state 2, right? It needs to know that, for example, if I did this loop on state 1 2 times, then if I did this 2 times, I should do this 2 times to have a balanced parentheses. But the finite state machine just doesn't have any memory, so it can't actually remember that. So let's look at what a context-free grammar looks like. Let's define it formally first, and then I'll show you some examples. A context-free grammar, or CFG, consists of a set of terminal symbols, which is all of the input symbols that you'll see. And in a compiler, the set of terminals might be the tokens that you have defined in your lexical analyzer, right? So the input symbols could be like T, identifier. In the examples that we'll do, when we introduce context-free grammars, we'll just assume that the terminals are similar to the alphabet that we defined in regular expressions. So we have a finite set of terminal symbols. So these are our atoms that we'll build to create longer and longer strings. Then we have a set of non-terminals, and this is a new set, and it's comprised of symbols that don't appear in the input. So these are kind of meta level symbols that we will use to manipulate the input, and you'll see what we mean when we see some examples. We have a special symbol, which is the start symbol, and start symbol is an example of a non-terminal. So it's one of these abstract symbols that we'll use. And then finally, the main sort of bulk of the context-free grammar is how to take these sets and use elements of those sets, the set of non-terminal, set of terminals, and use it to build a set of rules. And these rules, they're also called production rules or productions sometimes. They comprise of a left-hand side and a right-hand side. And the left-hand side is always an element from the set of non-terminals. And the right-hand side is any mixture of non-terminals or terminals, and you can even have the empty string. So you could say that a certain non-terminal X has on the right-hand side just the empty string. So these are how you can build these rules. And what does a rule mean? So you can apply a rule by taking a left-hand side. So if I see an X anywhere, I can replace it with the right-hand side. So essentially I'm taking this left-hand side, and the rule application says I can replace it with whatever sequence of symbols appears in the right-hand side, and vice versa. So you can take a sequence of symbols in the right-hand side and replace it with the left-hand side. And we'll see, depending on the direction, we might go in one direction or the other in order to do a parsing of a program. So a context-free grammar is defined in that way, but let's look at a concrete example so that you can understand all of the various sets and the rules and what they mean. So let's look at a language. So as we saw before, we know that a language is just a set of strings. So in this case, it's a set of strings that consists of balanced parentheses. So if I was to expand this out, it's I greater than or equal to 0. So I can have 0 parentheses, open and close. They're both 0. Or I can have 1 open, 1 close. I can have 2 open, 2 close. I can have 3 open, 3 close, and so on. So this is a concise way of writing down this infinite set of strings where you can strictly have some open parentheses and then you have to have an equal number of closed parentheses. So how do I recognize this language using a context-free grammar? As we had defined before, we have a set of rules. So we have 2 rules, and the left-hand side consists of a non-terminal. These 2 left-hand sides are the same non-terminal, which is S. So in fact, there's only one non-terminal in this grammar. So the set of non-terminals here consists of exactly one element, which is capital S. And this is the non-terminal we'll use to define the grammar. And then we have a left-hand side here and a right-hand side here. And the left-hand side is S, and the right-hand side is open parenthesis, S, close parentheses. And these open and close are terminal symbols. And on this right-hand side, you can see that the S goes to the empty string. So essentially, the S gets replaced with an empty string, thus removing it. So here, the terminal symbols, not including the empty string, is open parenthesis and a close parenthesis. And I'm going to put these quotes around it just to emphasize that they are characters that the grammar recognizes in the input. So notice that there are 2 S rules. They both have S on the left-hand side. So here it's a non-deterministic choice of which rule you can pick at any point. So this context-free grammar is an example of a non-deterministic rule choice, right? So it's similar to an NFA by analogy. In this case, the choice of S rule determines which string you would generate. So let's look at some examples. One question that you can think about to make sure that you're understanding is whether that string that's shown over here, it belongs to this language that's defined here. So it's either true or false. You can look at the definition of that language and see, does this string belong in that set of strings? Another question you can ask yourself in order to tell whether you're understanding is to modify this grammar that's given here, which is only over round parentheses here, and extend it to use a bigger alphabet here of different types of opening and closing parentheses, but a opening parenthesis of one type must have the same type as the closing parenthesis, right? So this would be valid, but this is invalid because it opens with a round bracket and closes with a curly bracket, and that's invalid. Try to write down a grammar that is a modification of this one that will have this extended alphabet or set of terminal symbols. So let's look at how this context-free grammar would actually recognize the set of strings that I mentioned, which is balanced parentheses. So if you have a bunch of open, you have a bunch of closed parentheses, and that's all it recognizes. So let's see how it does that. Let's begin with a string that only has a start symbol S, and then you can take that S and replace it with any of the rules that are in the grammar. So if I have any non-terminal X in this string, I can take that non-terminal X and then replace it with the right-hand side of any rule that occurs in my context-free grammar. And I keep repeating this until there is not even a single non-terminal left. So I have to replace all the non-terminals eventually with just terminal symbols or input symbols. So let's look at the grammar again, and I just numbered the rules. R1 is S goes to open parenthesis, S and close parenthesis, and I'm omitting the string just to keep it simple, but those open and close parentheses are terminal symbols, right? And so R1 introduces an open and close parenthesis, and R2 gets rid of the S by replacing it with the empty string. So what we can do is choose the start symbol, which is S, and then apply any rule, R1 or R2. Let's say I choose R1. Then I replace the left-hand side S with this right-hand side. And I can do this non-deterministically. I can choose either R1 or R2. So let's say I choose R1. So that's this choice over here. And I get the right-hand side just copied over, right? Now I can apply rule R1 again. And I get this S replaced with this right-hand side again. So it's that part which is getting replaced over there. And now I can take this S over here and apply rule R2, which is taking this left-hand side S and replacing it with the empty string. And notice that the empty string here is essentially invisible, right? So I don't have to write it. It's a string of 0 length. So in the end, what I end up with is 2 open and 2 close parentheses. And I could have kept on using rule R1 to generate more and more parentheses. That's your choice. So it's a non-deterministic choice, right? So if you choose 3 applications of R1 and then R2, you would end up with 3 open parentheses and 3 closed ones. Notice that the grammar always makes sure that the opening parenthesis matches the closing parenthesis because they're introduced in the same rule. So this sequence of rule applications is what we call a derivation. And this notation here of this double arrow is used to denote one rule application. Obviously, every string that you generate will involve one or more than one rule application. So you could have multiple ones, one after the other, until at some point you do not have any non-terminals, and then you can't apply any rule anymore, right? Because they've replaced all of them with the right-hand side. So each of these derivations can be drawn as a parse tree. So that's where we get a parse tree from, is just from a derivation, which is each step is a rule application. So we start with the start symbol, which is the root of the tree. And then for every production, we add the children, the right-hand side, as children in the tree to this node X. So if I have a rule that looks like this, then the parse tree ends up looking like this. Now let's look at an example derivation and parse tree. So the same example that we saw before, we start from the start symbol S. We use one step in the derivation, and I use rule R1, and I expand it using rule R1 to get an open bracket, S, and close bracket, right? So that's the right-hand side of the rule R1. And notice that I can draw that as a tree structure over here. Now if I apply rule R1 again, I'm expanding this S here using rule R1, which again expands it with open bracket S close bracket. And then when I apply rule R2, S goes to the empty string, which we don't need to write out because it's just the empty string. So one useful notation that we'll use is the notion of a closure of this double right arrow here. So if I have 0 or more steps in this derivation, so I have 0 or more double right arrows and in my derivation, so I'm doing one rule application after the other, I can say that if I did it once, twice, 3 times, I can replace that with S in 0 or more steps can derive 2 open and 2 close parentheses. So this definition is going to be useful to us because often it's tedious to write down the entire derivation. And sometimes you can say, oh yeah, I can see that if I apply the grammar rules 0 or more times, I can get this string or this sequence of strings combined with non-terminal symbols. So in fact, this is also a true statement where I have S in 0 or more steps can get to here, and then I can apply R2 and then replace it with the empty string. So I could use the closure of the derivation with the star. So S in 0 or more steps can get to a string. It doesn't always have to have no non-terminals. It can have a non-terminal. And then from that, I can sort of take another step and get to the string, or many more steps as well. So the number of steps I need to take in this is not bounded, right? I can do 0, I can do 1, 2, as many as I want. As a test for whether you're understanding, write down the derivation and parse tree for this nested parenthesis grammar that you wrote on slide 6 for these sort of different types of parentheses. Okay, so just like we had regular expressions were equivalent to regular languages, there is also a notion where each context-free grammar corresponds to a language, a set of strings. So what is the language of context-free grammars? So if G is a context-free grammar with the start symbol S and terminals T, the language of G, which just like we did for regular expressions, we'll call L of G, right? So this notation is identical to what we did for regular expressions. It's just a set of strings that you can derive using 0 or more derivation steps. So you have to start with the start symbol. So S here is the start symbol. Application of rules happens 0 or more times, and in the end you end up with a sequence. We just need to make sure that each element of this sequence is a terminal symbol. So basically there are no non-terminals because it's a set of strings, and we don't have non-terminals in the set of strings. And so this set defines the language of the grammar. So let's look at an example, the same example we've been using all along. So you have this two rules in the context-free grammar. If I want to define the language of this grammar, let's call this grammar G1. How do I define the L of G1? So let's call this G1. The L of G1 would be either I can apply rule 2 and I get the empty string, or I can apply rule 1 followed by rule 2, and then this is the one we've seen before. I apply rule 1, rule 1, rule 2. So I do rule 1 twice and then rule 2, and then this one I apply rule 1 3 times, and then I finally follow up with a rule 2 application to get rid of the S that's going to be in the middle of that, and so on. So I can just keep going and apply R1 n times followed by R2, right? So that defines my set of strings, which is the language of this grammar. Okay, so let's look at a non-trivial example of a context-free grammar, or at least something a little bit more complex. And let's look at the grammar of arithmetic expressions, where for the sake of this example, I just care about addition, multiplication, and unary minus. This one is a unary minus, this is a multiplication, this is the plus. Notice that here, the plus and the times, the asterisk here is used for the times, and the unary minus, the parenthesis, and the ID for identifier. These are all terminal symbols, right? So in this case, if I was to write down the terminal symbols for this grammar, I would get plus, times, open parenthesis, close parenthesis, minus, and then ID. I'm assuming here that the ID comes from some lexical analyzer, so it knows, what a proper identifier is, and it might even give me the value of that identifier. If you look at what the non-terminal in this grammar is, so if I look at the set of non-terminals, you can see that there's only one non-terminal, E, and here we're assuming that the start symbol is equal to E. So we're going to start from E, and then we can derive various arithmetic expressions. The plus and the times and the minus are not mathematical operators here. They're actually just characters in a ASCII input, right? Or, in the input program, these are just strings. They don't have a semantics yet, which we want to define that, but that'll come later. So let's look at an input string. So ID plus ID times ID. And this is my grammar over here. And the first thing I'm going to do is start from the start symbol. So I can start from E, which is my start symbol. And I do one rule application. So notice that I could choose any one of these rules can be chosen because it's not deterministic. So let's say I chose this one over here, which is E gets replaced with E plus E. is not an unreasonable choice because we know that there is a plus here. So eventually we do need a plus, right? So it's a good idea to use E plus E. We know that the input string has a plus in it. Now we can take the first non-terminal here and take any one of the E rules again. So it's a completely non-deterministic choice, but I can see that if I want to parse this input string over here, then that E should probably choose this rule, right, in order to get ID plus, which is the first two symbols in the input. So that's what I'll do. And then I can replace this E with any choice. I know that I need times, so I'm going to choose E times E. And then the next step is I want to change this E to an ID, and then I now have to expand this E, which if I expand it to an ID, will give me the string that's my input string. So you can think of this string here as your input, and I want to be able to find the structure of this input given this context-free grammar. So if I was to draw this out as a tree, like we saw before, we can see that this derivation corresponds to a tree structure where the multiplication happens, and then the result of the multiplication is added to this identifier value, and that final value is at the root of this tree. So you can see that the tree structure is exactly a graphical description of this derivation sequence, right? So it's just one rule application after the other. So the leaf nodes are terminals. So if I look at these leaf nodes here, they're all terminal symbols. And if I look at the interior nodes, we know that there is only one non-terminal here, which is E. So all of the internal nodes here are that non-terminal, which is a capital E here. The notation again is that in 0 or more steps, I can start from the start symbol E and then derive this input string ID plus ID times ID. Is this the only way that we could have done the non-deterministic choice of which rule to apply? Notice that we are constrained. We still need to be able to recognize this input string. So it's not like we can choose this one, right? Because the input doesn't have a parentheses in it. So if I choose that one, I won't be able to recognize this string. So I'm constrained by which rules I can choose. But do I have another way, another non-deterministic choice that still is a valid derivation? So let's look at a notion of a leftmost derivation for ID plus ID times ID given this grammar over here. So leftmost derivation, all it means is it gives you a constraint on which non-terminal to expand at any point. It starts off with the start symbol, and it expands this one using the times rule, right? So it gives me this. I'm constrained in a leftmost derivation to always pick the leftmost non-terminal. It's a leftmost one, not the left one. So whichever one is the leftmost is the one that we'll pick. So in this case, this E that's marked in red over here is the one that I need to expand. So if I choose from any of the rules, I know that I have to choose E plus E, otherwise I won't be able to recognize the string. So that's what I'll do, is I'll replace this E here with the first rule, which is this one, and I just replace it with the right hand side, so I get E plus E times E. And now I can take the leftmost non-terminal, which is this one, and replace it with an ID. Now the leftmost non-terminal is that E, right? So if I look at this sequence of strings, this was the leftmost one here, this is the leftmost one here, and now I replace that with an ID. Now the leftmost non-terminal ends up this. It is the rightmost symbol, but it is the leftmost non-terminal, right? So if I look at this, there's no other non-terminal until I get to that point. So that's why it's a leftmost. And if I replace that, I get a successful parse of what I want to recognize, which is ID plus ID times ID. Now, if I draw the parse tree for this sequence of choices, it's different from the one I did before. I end up with a parse tree that looks like this. So notice that here, the reason when I chose this expansion over here, e goes to e plus e, it happened. So notice that I have e times e over here, which is corresponding to this. And then this expansion of e goes to e plus e is this part over here. So this corresponds to this choice here. And notice how this time the addition is happening first and the multiplication is happening on the result of the addition. So what went, I guess you could say something went wrong here, or whether the grammar doesn't really care about precedence, right? There's nothing in the grammar about precedence rules. It seems like a perfectly valid tree to this context-free grammar. We have to add something extra, precedence, for example, in order to derive the correct parse tree. So the parse tree here disambiguates the operator precedence, right? So these subtrees are just brackets. So in this case, I'm getting the addition happening first and then the multiplication. And in the previous choice, it got the multiplication first and then added the first identifier value to it. So this is the one we prefer, obviously, and we don't want this one. But the context-free grammar at this point gives us both as valid choices. Along with the leftmost derivation, we also can have a notion of a rightmost derivation. And again, it's just to be consistent so that we're always replacing a consistent non-terminal every time. So we are not just confused by, replacing different non-terminals in different orders, because when we do that, they end up not being any different in the parse tree. So a rightmost derivation is kind of like the flip side of a leftmost derivation. You always replace the rightmost symbol, the rightmost non-terminal. So if I start with the start symbol, I use the times and I replace it with the right-hand side of that rule. I get e times e. And now instead of the leftmost symbol, I just replace the rightmost symbol. So I would get e gets replaced with id, right? And notice that I'm kind of forced to make that choice, because if I chose e goes to e plus e, then I would not be able to derive this input string, right? Because I want the addition to come before the multiplication, not after. So this one is ruled out as a choice. So even though I have a choice, it's not deterministic. Some of the choices are ruled out because of the input string that I have to parse. And then I take the rightmost symbol, which is this e here, and I replace it with e plus e, which is the right-hand side of this rule. And now I just replace the e's with the identifier token, and I get id plus id times id. So this is non-negotiable. I need to get that same input. The input string has to be identified correctly, right? No matter what choice of rules you take. So in the end, if I take this sequence of rule applications and I draw out the tree structure for it, I get the e gets replaced with e plus e in the context of the times e, right? So that's the parse tree here reflects this choice of rule applications. And there is another rightmost derivation that should give you the same parse tree that was the correct one, or the one that we prefer based on the precedence rule. So what I want you to do is, in order to make sure that you understand this, is do a rightmost derivation. So always replace the rightmost non-terminal and get the other parse tree where the multiplication happens first, and then the result is taken to you're adding that result to the next identifier. So in order to check that you understand this process, what I would like you to do is write down a rightmost derivation using the same grammar, but using a different choice of application of rules. You're choosing a different rule and replacing it. You still have to get the same input. So id plus id times id, but you want to get the other parse tree, the one where the multiplication happens first. So what's the difference between a rightmost and a leftmost derivation? Well, a rightmost, there are equivalent rightmost and leftmost derivations. Right? So every parse tree has a rightmost derivation, and every parse tree has an equivalent leftmost derivation. So just by having two different derivations is not enough. There have to be two different leftmost derivations or two different rightmost derivations. And so in order to resolve ambiguity or talk about ambiguity even, we need to say that a input is ambiguous if and only if it has two different leftmost derivations. Like at some point you have a non-deterministic choice that leads to a different derivation. And the same is true for a rightmost derivation. But if an input has one leftmost and a rightmost derivation, that doesn't mean it's ambiguous, right? It has to have at least two leftmost and at least two rightmost to be ambiguous. Okay, so how do we take a context-free grammar approach to writing a parser for a programming language? So we first kind of look at the reference grammar or the specification of, or you can write one yourself, of what you want to be the valid programs. So you have to write down what is the definition of this programming language. For now, we'll just worry about the structure. So this reference grammar might choose to overgenerate in cases where this is not a valid Boolean value, but it doesn't care about that right now. It just cares about the structure of the program rather than the semantic errors that might occur. So this we would consider to be a semantic error because X is defined as a Boolean and should really be only assigned true or false, right? Not an integer. Then we take this reference grammar and convert it into a context-free grammar. And then use actions for each context-free grammar rule to produce the output. So the actions are triggered every time you successfully recognize a rule or you use a rule in a derivation, right? So when you're doing a rule application, each rule will have some kind of action that gives us an ability to do something useful. So let's look at actions in a CFG using this example. And we're going to continue using arithmetic expressions as an example. All right, so we have the same grammar as before, right? So this should look familiar to you. But then we have this part over here, and this is the part that's new, and these are called the actions associated with each rule. So each rule in the context-free grammar has an associated action that triggers when you use that rule in a derivation. So let's see how that works. And it has a sort of notation there so that it can use the values that are generated by whatever is in the right-hand side, right? So I'll explain that using this example. So let's start with the derivation, which as we know, you can write down as a parse tree. The input was something like 2 plus 3 times 5. Let's say that we know the values of these identifiers and the values are just numbers so that I can use it in this example. So the first thing we do is calculate the value of this non-terminal and this one. And we know that those are 2 and 3 because we get the value from here, right? And then we can add those two values and get the value of the non-terminal that's over here, which is the parent or the left-hand side of the rule that was applied. So now we have 5 as the value, which is the result of adding those two numbers. Then we can look at this part over here, which takes the number 5, which is the last identifier, and propagates it to this non-terminal here. And what it does then is combine those two numbers to give me, so multiplies them because it's using the times production or rule. So it multiplies those two to give 25, right? So how does this work in terms of the actions? Well, we're going to use these variables over here. So this variable, I'm going to explain it to you using the multiplication rule. This $$ variable stands for the value that we're going to assign to the left-hand side based on the values I compute from the right-hand side. Okay, so in this case, the left-hand side, E, is going to get the value, which is the product of these two values that I computed for that E, and that's called $1 because it's the first symbol on the right-hand side of this rule. That's why it's called $1. And then it's going to multiply that with $3, which is the third symbol, right? So here, $1, that's $3. And notice that this is $2, which doesn't really play a role here because we already know that it's multiplication. So I'm just going to use the multiplication operator here. Notice the difference is this is times, but it's the character, the asterisk, in fact, which is the input character for the multiplication operator. This one over here is the actual multiplication that's happening in C, okay, or whatever code that you generate. So that multiplication is a real mathematical operator. This is just a string, a character for times. So that's how I can use an action. So this E goes to E times E rule. This $$ is the node that's a parent. This is $1, which is this one over here, and then this is $3, which is this one over here. And you can take the value 5 times 5 and then compute $$ equals 25, and that gets passed up. And when you go to the root of this tree, it will give you the end result of this arithmetic expression evaluated for you using this context-free grammar. So in order to check that you understand how actions work, I want you to draw the parse tree using the same grammar and the same set of actions. Write down the parse tree and calculate how it would compute the value of minus and then open brackets 2 plus 3 close brackets. And one thing to pay attention to is whether or not this input string is ambiguous. Does it give you different answers, or does it give you exactly one answer based on the derivations that you can get for that input string? Before we go into more details about context-free grammars and how we can write a parser with them, let's just talk about notation. So I've been using this notation to write down my context-free grammars. There's a left-hand side, and then there is an arrow, and then there is a right-hand side. And there's always exactly one symbol on the left-hand side. That's just because of the definition of context-free grammars. There is some alternative ways you can write down this. Notice that these two are both E rules. So in order to group together all the rules that have the same left-hand side, the Backus-Naur notation uses this kind of OR symbol. So this gets converted into E times E, and then this OR symbol, and then E plus E. And then just to terminate it, you put a semicolon. You can also have variants of this, which ends in a sort of period. It's just a convention, right? As long as we know that this alternation stands for multiple rules with the same left-hand side, and we know what the statement, the terminator character is. It's just a special character to tell us, okay, I've finished seeing all of the different E rules, and it can be a period or a semicolon. It doesn't really matter. So next we're going to look at how we can write a parser once we have a context-free grammar. And the parsing algorithm will then be the way that we apply these actions to do various things. In the end, we want those actions to do code generation for us.